Yeah. Hope I'm like audible. Right?
Yes, we can hear you.
Okay. So welcome to the intro to control system. So today like we will be seeing about like the I think most of you might know like what will be the this thing. So we'll be seeing about the overview of a control system. So what are the control system and so. So before going into the what is meant by control system, I would like to say something about the robotics competition. So in which we will be teaching like so many technology stacks. So the timeline for the EYRC will be like it starts. The registration is from like 1st to 25th. Start from 1st August, and registration will go till 25th August. Okay, and EYRC will be having like two stages: stage one and stage two. And after stage two, it will be finale, which will be in the month of March. And the stage one, which is a software based stage, so only you'll be learning the tech stack in the software. So this will be going around like from September to November. And based on the performance of the stage one, only few teams will be like taken for the stage two. So which stage two will be like a hardware based task. So in stage two, like you'll be having like a four task based on each and every theme. So based on the performance of the theme in the stage two, you will be like selected for the finale. And uh, you'll be like coming to the IT Bombay, and you'll be like showing your particular tech stacks uh, demo. So before like show the previous year ka video. This is a remote hardware based robotics. This is a polynomial field for solving complex problems. This is one of the control systems which uses the reactivity balance and it's following the line. And this is the programming based using programming as code or like based processing. And so the after the finale, so you'll be getting a so these are will be the goodies like the end we'll be getting goodies and cash prizes, and moreover that you'll be getting a 8 weeks ka paid internship at IIT Bombay. And this is how the portal. So yeah, so this is how the portal looks. So we'll be updating this, so you can see that. And also like we are planning like we are going to conduct a cross to move. So the registration is ongoing. It will be till July 18th. So you can register to this course and you can learn ROS 2 online. Okay. So now we are going to get into the like the today's agenda of the intro to the control system. So before showing the concept, so I would like to show the previous year's video of control systems. So this is the normal presentation for legacy tools. So it's back to our like so it is like using its wheel to balance memory. Using another magnet. And this will be I think there's some issue with the internet. Okay, so we'll be Yeah. I think there's some technical issue from our side. So I think now it's clear. Can anyone verify?
Yes, we can hear you, Jerish, and we can see you also. I
Yeah.
think
Okay.
you'll have to share your screen.
Okay. Okay. So yeah. Hope the screen is visible.
Yeah, you are audible. It's
Okay.
visible also. Camera is also visible.
Okay. So let's start with the system. So a system is like comprises of a component, like many components, which are like uh, which perform like together to perform some task. So it will be like interrelated and it will be like working with the others to perform some task. So this is called a system. So you can take any systems. For example, like whatever things like maybe a car. So in a car you will be having different components like a steering, a brake, a accelerator, a fuel tank, and radiator, and so many components which are like a miniature component, but they are interrelated to each other to perform some tasks. So these are called a system. Now, now we need to think about like what is a control system. So a control system, it's like the system is like can be like anything like whatever you're saying. So it performs some tasks. But if you want to perform some tasks in a controlled environment or like in a controlled manner, so that's where the control system comes into play. So there are like two types of control system. Yeah. So there are like two types of control system. So open loop system and closed loop system. So in an open loop system, so it can there will be like a controller which is will be taking input and like it will be doing some uh, time based task, or it can be any task, and it will be giving an output which is like a control input to the plan, and the plan gives us output. So in an open loop system, the output of a system does not depends on the uh, sorry the output action cannot be like rectified if there is like a some so the input is like being cannot be like changed to the plan based on the output. Okay, so if the output is like, so we need to assume like the output is like perfect and like there is no feedback or like a no response from the output side which can like turn which can change the controller output. So in case if you can think about like a example like a microwave. So what does the microwave does is like a, so you'll be keeping a food in a microwave. It will be like a timer base. So it will be after some time. Okay, it won't see like whether the uh, food is actually cooked or not. So it will be just okay after the time. It is like giving some kind. Okay, it will be assuming like a the work has been done. So that's how so that's one of the example of a open loop system. So similarly, there will be like a so there's other type of system which is called like a closed loop system. So in a closed loop system, so there is like the input to the plan is like depend on the output of the plan. So here we uses like a so you can see a loop which is called like a feedback loop, which has been taken from the output, and it has been like checked with the input. So here usually we call this input as some kind of reference. So what, so we'll be giving an input which is like what the output should be. So the reference output that we require is like fed as an input. So what, so this feedback element can be any sensor, like for example it can be camera or any sensors like which is like measure, it can be a thermometer in case of like measuring a temperature, or any sensor which can like interact with the environment and get the feedback from them. So that's what this feedback loop does. So it will be taking an output, and so it will be like try checking with the input, and the difference of this will be considered as an error, and this error is given to the controller. So this controller, so which will be like deeply learning in the next session. So so I'm not going to tell more like much thing about this controller. So what this controller does is like it will make a decision based on the error it's been receiving from the uh, difference from the input and the output, and it will be feeding it to the plan. So you might you also can see the some disturbance signal. So something which is like called as disturbance signal, which is given here. So first we can just consider there is no disturbance. So I'll be coming back to what is this particular disturbance signal. So before that, I'd like to say about, so what this control signal does is like, so just for now you can consider this to be 0. So what this control signal does is like, it will be like directly given to the plant. So as far as we know, like in the open loop system also, so whenever there's a control input is given to the plant, so it will give an output. So similarly, now it gives an output. But if this output doesn't match the reference input, so now we have a feedback. So which will basically correct, it's based on the error that is being like, which is the difference of this thing, input as well as the output. Okay, and now we can come back to the disturbance signal. So what is disturbance signal? So this can be like considered some kind of unwanted inputs that can be like given, like it can be given to the system, or like it's like given to the system by the environment. So we can say like in case of like okay, so I can come up with like some like a example of an air conditioner. So just consider that there's an air conditioner and it's like a well closed room. So what this air conditioner does is like the, so you no need to just consider it's like a well considered room, and you know like how much time it take to actually uh, cool that particular room to that like desired temperature. For example, like 24 degree or 25 degree. You might be doing some calculation, and like you know like how much time the particular air conditioner should be turned on to make the room cool, and like how much time it needs off. So in that case, it will be like a, it looks like a normal open loop system. So you know, so there is an input which is the temperature required, and you are designing a controller. So, and this controller knows like okay when to turn on and when to turn off without the feedback. So that's how the not the air conditioner, which is like a in a well closed room. So now consider there is some kind of there is an air conditioner, and there is some kind of uh, the door has been, there's some leakage of, or the doors has been opened, or the window has been opened. So in that case, whatever the calculation you have, you might have done the calculation assuming that the door has been closed, right? So in that case, so whatever the calculation done here will be, the output won't be maintained at that temperature, because there is some kind of uncertainty that has been created by the environment, which can be considered as like a uh, disturbance signal, right? So this kind of situation can be tackled by a closed loop system and not the open loop system. So this is the major advantages of the closed loop system. So the most of the control, it's like if you want like have a good control over a system, so most of the system will be like a closed loop system under a very closed environment, and like a very certain environment, this open loop system performs better. Okay, and when compared to the complexity, open loop system complexity will be less than the closed loop system complexity, right? And these are the broad classification of the control system. So these are, so there are other types of control systems in control system, so which we call it as CISO, MISO, MIMO, and MISO, which are like single input single output, and single input multi output, single multi input single output, and multi input multi output. But here I have like listed two of them. So let's see what is that. Yeah, so let's see what's that. So CISO system, so what it does is like, so it will take a input. So there will be only one input to the system. So as we saw previously, so a single input is given and a single output is given. So that systems are called like a CISO system, right? So for example, you can consider an example of a cruise control of a car. Like you need, like given acceleration, and based on like you need to press the accelerator. That's a single input, and the output will be the motion of the car, right? So the other type of system is like the MIMO system. So there will be multiple input and multiple output. So in case of like, so there will be like so the input will be like multiple. So in this case, you can consider an example like quadcopter. So the quadcopter, like there will be like a four propeller. So four propeller require like four different velocity at which it needs to rotate. So that can be like a four different, and also like the output will be like its roll, pitch, yaw, and its thrust, like how much height it needs. So like multiple outputs also there in that drone system. So that system, so the drone system comes under the MIMO system. Yeah. So this is a state space modeling. So before going to the state space modeling, so why I would like to say like why we require state space modeling. So you might, so I have told like these are the like there are like four type of system, out of which these are the like most like common type of system. Okay. And so there is like other approach called like a transfer function approach. So that what does the transfer function approach does is like it will convert the differential equation to a like S domain using Laplace transform to convert to S domain, and there will be like a Laplace transform of the output divided by the Laplace transform of the input. So the transfer function approach will be like applicable only for like a CISO system, like a single input single output system. So it cannot be applied to a multi input multi output system. So this difficulty has been overcome by a method called state space modeling. So here you can see like a two equation you can see like state equation. So x dot, so we'll be having like our state. So first of all, like before going to the state space model, I would like to say what do you mean by state. So state is nothing but the internal behavior of a system. So you can see about like, for example, like in case of like a pendulum, or else, let's consider a car. In a car, so what are the things that it can be considered as a behavior if it's a moving? So the position of a bot and how fast the car is moving, and at what acceleration the car is moving. So these kind of behavior of the system is considered as a state of the system, and the state should be like a minimum variable which required to the describe its internal characteristics of the entire system. So this x vector will be having like a behavior like position, velocity, or acceleration, etc. So it will be having the states which are like minimum states which are required to like entirely describe the its internal uh, dynamics of the system. Okay, so that's what the x has, and u is nothing but the input vector. So which will be like a, so basically like in a car, like you will be having like a accelerator which is given to an input. So this u vector which will be like a which can hold like a multiple values, and that so this vector will be mapping the input to how the state is been like evolving. So x dot is like the derivative of a state, so how the state is being evolved. So this u input, uh, the input vector, which is like how the input is varying with respect to the state, which has been like mapped by a matrix called B matrix. Similarly, how the dynamics or the state is been varying varying with respect to time is been mapped by the matrix called A. So so here you can see that the x, y, and u, which are the small letter or the vectors, and the A, B, C, D, which are the matrix. Okay, and this A matrix maps like how your state is going to evolve with respect to time. Okay, and the output equation. So why is your output? So you, the previous also you might have seen the output. So how your output is like varying with respect to your state is being mapped by the matrix called C, and how it's been how the input is directly varying with respect to the output. So how the input is affecting the output is being mapped by D. So in most of the cases, in even in the pre, so there is no direct link between your input and the output. Okay, so actually you're giving an input to your system, and like most of the system, so the system will actually varies the state of the system, and that state will give you a variation in your output. So it's like an indirect way of like actually like changing the output. So most of the case this D matrix will be like a zero. So I would like to show you some example to show like how the state equation, like a simple example to show how the state equation can be like done from your normal dynamics equation. Okay, yeah, so just let's consider a simple pendulum. Okay, so the simple pendulum, so just consider yeah, so this is the derived dynamical equation of the simple pendulum. How the if you're like having an initial condition and if you're leaving the pendulum, so it will be like moving to and fro, like it will be swinging. So that is been described using the this particular equation. So this is the dynamical equation. Okay, so this so we are having the variables theta double dot sine theta and g. So these are the variables. So now we need to see how we can map. So you can see there are like uh, multiple variables are there. So basic at least the theta and theta dot in this case. So this both are considered to be the state. So this x1 and x2 are nothing but the as a x vector. So it's having two values, x1 and x2. Okay, now we are going to rewrite. So this is nothing but the so we have rewritten the this particular equation into this. So first x1 is nothing but theta, so x1 dot will be theta dot, and x2 dot will be like equal to the x1 dot, the previous x1 dot, which is nothing but theta double dot, which is the same dynamical equation. So you can see the same equation here. So now you can see like why we are not doing this, like taking already there is a state x1 x2 and uh, x1 dot x2 dot y. So you might have seen in the left hand side, so there is like a derivative of the state, so it should be like a x1 dot and x2 dot. So in order to like map your how your state is varying with your time, so that's why like we are like writing in this particular systematic manner. So x1 dot will be equal to theta dot, and x2 dot equal to minus g by l sine theta. And the system that we are seeing, so this system is actually a nonlinear system. So you can see it's like the relation between the input and output is not a linear combination. So it's like there's a sign term which is causing it to have a non-linearity in its nature itself. Okay, so what we does is like in order to like implement the uh, so there are like controllers called like so most of the system that we are seeing in the nature are actually a non-linear system. Okay, so but the nonlinear systems are like too much complex to learn, and also like it's very complex to design a controller for a nonlinear system. So what we does is like we will linearize the system, and we can implement the normal linear controller which are like applicable to that particular linearized nonlinear system. Okay, so that's what we are doing. So what we are doing is like, so for a pendulum there are actually uh, two equilibrium points. So equilibrium point, you can say like if you're like the point at which it will be like the relative motion will be like a zero, you can say, of like a pendulum at least. So in this pendulum, so if you consider this to be like a 0 0, so these are the angle. So this is a 0 0, and the top angle is the, so if you have upright angle, so that's like a pi, like 180 degree. So in a simple pendulum, the equilibrium point is like the 0 0 point. That will be the considered as the equilibrium point. Okay, so so this the conversion of the nonlinear system to a linear system, like you will be linearizing around some equilibrium point. So in that case, the sine theta can be considered as theta and cos theta can be considered as 1. Okay. Now you can see like, okay, so after linearizing, you can see this particular nonlinear equation has been turned. So we have like linearized the sine theta, so which is turned to be like a linear system. Now you can see like only theta dot and like just theta. So now if you are writing in terms of like in the previous equation, the state equation, x dot equal to ax plus du. So x1 dot and x2 dot. So this x1 dot is depending on theta dot. The theta dot is nothing but the x2. So there is no relation with respect to the x1, and there is like a direct relationship of this dot with respect to x2, because x1 dot is the theta dot and x2 is the theta dot. So 1 to 1 relation. So 1, and like the similarly for x2 dot also. So now you can see some kind of like structure which is you have already been seen has been there. This x dot equal to ax, but still we are like missing the u. Can you guess like why we are like missing the u? Okay, so because like there is no input, so just the initial condition and So this simple pendulum is based on the principle like you are like having an initial condition and you are living from the initial condition. So it will take so it will like keep on moving without any external forces. So no force has been given. But if you consider inverted pendulum, so there should be some kind of external push should be there not to make it balance or like to keep it in its equilibrium like the other equilibrium point. And I would like to say about like there are actually two equilibrium points. So one is like a stable equilibrium point and other one is like unstable equilibrium point. So the stable equilibrium point is like if you're like moving a object from its stable equilibrium point, it will come back to its the equilibrium point. So that's called like stable equilibrium point. So in case of like a simple pendulum, if you are like having like moving it from its 0 0 to any direction, it will tries to come back to its 0 0 position. So that's called it stable equilibrium point. The other equilibrium point. So if you're taking it 180-degree, the and leave the system, it won't come back to its like the 180-degree. It will try back goes back to the stable equilibrium point, right? So unstable equilibrium point is considered to be like a force is some kind of force is required to keep it in that particular unstable equilibrium point. So even for a small change in if there is a small force which act on that when it's in the unstable equilibrium point, it will make the system move towards away from the equilibrium point. In such case, that equilibrium point is called as the unstable equilibrium point. Okay. So in the simple pendulum, it's like equilibrium point. So now we are like considering for a inverted pendulum. So it will be the equation will be more or less similar. So you can see the previous equation. So it will be like more or less similar equation, but there will be like a force term which is the T will be added. So now the uh, state space equation will become in such a manner. So left hand side is it can be like x dot is equal to, so this matrix is the A matrix, this is x and plus, and this is the B matrix and this is the U. So now you can see like so multiple uh, inputs has been like so multiple variables are have been like very systematically incorporated into the particular representation. So based on this particular so why we need to learn this representation? So based on this representation there are like uh, so if you can like make your system into this representation, you can like make implement there are like so many linear controllers which you'll be seeing in the upcoming session. So you can implement the linear controller with the help of this representation. So this is just like a overview of like how this representation looks like. Okay. So we have seen like so in control system there are like a two important control in a state space model. So it's like a controllability of a system and observability of system. So both are like how like you are like so B matrix will have the information of the how your input has been like uh, varying or the like influencing your state rate of change of state, or and the A is having how your state is been like changing with respect to time. So with the composite of both you can actually like so there's like a procedure for finding like whether with this particular input you can control your system or not. So this is how this is done. So this we call it as controllability matrix. So the system is considered to be a controllable matrix if and only if like the rank of this composite matrix. So this B which is having the information of the input and AB is having the information. So AB is like the multiplication of the A matrix that you might have seen in the previous like this matrix with respect and this matrix the normal matrix multiplication, and like it will go on till it's so if the A is actually n cross n matrix, so you need to do it till n minus 1 and this system, and if it's turned out to be like a full rank matrix, then the system can be controllable. Okay. The similarly observability like how much state, so we might have seen output, so y is equal to yeah y is equal to cx, and for now we can just consider that d is actually zero matrix zero, and how this C is been so the state is been mapped to the output. So that is done by the C. So we need to know like how much the state can be absorbed from the output. Okay. So the observability matrix will has that data, and in order to say a system can be observable, all the state can be observable, the rank of this particular composite matrix should be like full rank. Okay, and yeah, so this is the overview of this. So I would like to show some of the simulate. So this is a simulator that you will be using in the stage one that I have previously mentioned, uh, to try out the digital twin of your physical model. So which is called CoppeliaSim. So it has Python and yeah, you can use Python and Lua, and we'll be teaching you the Python part. Mhm. Yeah, I'd like to show a small video like how it looks like. So it's like a kind of an inverted pen. Try to trying to balance. Yeah. So this is how the environment looks like. So you'll be like learning the. So you'll be using this in your stage one to learn the concept of the control system. Yeah. So now the scope of control system. So why we need to like. So you might have seen in the blog. So there is like a something called like in a closed, at least in the closed loop control system, there is like an error. So in everything that the system that we are designing, there will be like an error. So the perfection of a system can be achieved if we can like minimize or eliminate the error. So so this uh, so there are whatever system you take. So for example, uh, the robot that has been doing the acro, so it requires like a precise motion of like while landing, it needs to know like how much it needs to move to in order to like stabilize itself. It should not have any error. So basically the unbalancing or the destabilization of the bot is considered as some kind of error, and like the controller that we are designing should make sure that what kind of action should be taken so that the bot is not falling. The similar thing you can say it for a rocket also. So it's like when a rocket is being like launching, so there should be like, so it should like move in a particular trajectory to in order to achieve a in order to place the particular satellite in its location, right? So these are the, so it's like a very small. So there are like whatever system you can see, you can like there will be like an error wherever there is an error. You can like there's a scope of control system. Okay, and this is like a the map of control system. So you can see some of the circular parts. So these are the parts like which we'll be teaching in the theme. So what do you mean by like controllers like PID controller, LQR controller, how you can implement that to a system, and like the linearization thing. And apart from what we are teaching, there are like it's a broad field. Like you can see like the broad field, and like so just by knowing the important components of like how to like model the system and how system can be considered like controllable or not, or else like how you can like get a good uh, system output like based on the input that we are giving. So these are the basic things that we'll be teaching you. So and you are like allowed to, there are like so many unexplored regions where you can actually explore by yourself by learning this. Okay, so any questions?
Chat is now enabled. You can ask your question from chat.
So you can put your questions on the chat. Okay, so there are like some which is the best control system. So that depends on like which system like you are trying to control. So there's like some controller like depends on the design of the controller. So some system can be like easily controllable using a very simple controller. Like no need to like use a big expensive or like a complex controller, and with a simple controller you can. And if the system requires a complex controller, so you need to go for a complex controller. So it depends, and like what kind of application you are going to using it for. Yeah. Just a more common feedback loops or feed forward loops. So most of the cases, the feedback loops are being considered as like a most robust because in feed forward loops, so you'll be directly giving your like input is being like directly fed to the output like with the control input. So it's basically giving making sure that the uh, even if something like a problem happens, like for example if it want to perform some task and the task is having some problem, that problem cannot be considered in the feed forward loop, but in a feedback loops like you can have like based on the sensor data you can actually have a like from the output of your task you can get a feedback from that, and like you can like act accordingly. So most commonly used I would say it's like a feedback loop. Can you allow? Okay, the PAD and LQR. So actually, which will be like in-depth covered by in the next session. So there will be a session like in next Thursday. So in that the PAD LQR will become. Yeah. Anything else I left? Yeah. Okay, I think that's all. So okay, so the next talk will be on like introduction to PAD controller, 24th July. Okay, you can like see it in the yantra.org/talks. Okay. Okay. So before like end of the session, I'd like to have a quiz. So it will be like a 5 minutes quiz. So you can use the same name as you used in the WebEx. So it will be like enabled. It will put in the chat. Yeah. So I think it's been provided in the chat. So you can like start doing the quiz. So it will be like 5 minutes. So after 5 minutes, it will be like closed.